A multi-agent system is a computerized system composed of multiple interacting intelligent agents within an environment. Multi-agent systems can be used to solve problems that are difficult or impossible for an individual agent or a monolithic system to solve. Intelligence may include some methodic, functional, procedural approach, algorithmic search or reinforcement learning. Although there is considerable overlap, a multi-agent system is not always the same as an agent-based model. The goal of an ABM is to search for explanatory insight into the collective behavior of agents obeying simple rules, typically in natural systems, rather than in solving specific practical or engineering problems. The terminology of ABM tends to be used more often in the sciences, and M.A.S. in engineering and technology. Topics where multi-agent systems research may deliver an appropriate approach include online trading, disaster response, and modeling social structures. Concept: multi-agent systems consist of agents and their environment. Typically, multi-agent systems research refers to software agents. However, the agents in a multi-agent system could equally well be robots, humans or human teams. A multi-agent system may contain combined human-agent teams. Agents can be divided into different types ranging from simple to complex. Some categories suggested to define these types include passive agents or agents without goals, active agents with simple goals, cognitive agents. Agent environments can be divided into virtual environment, discrete environment, continuous environment. Agent environments can also be organized according to various properties like accessibility, determinism, dynamics, discreteness, episodicity, and dimensionality. Agent actions in the environment are typically mediated via an appropriate middleware. This middleware offers a first-class design abstraction for multi-agent systems, providing means to govern resource access and agent coordination. Characteristics: the agents in a multi-agent system have several important characteristics. Autonomy: the agents are at least partially independent, self-aware, autonomous. Local views: no agent has a full global view of the system, or the system is too complex for an agent to make practical use of such knowledge. Decentralization: there is no designated controlling agent. Self-organization and self-steering: multi-agent systems can manifest self-organization as well as self-steering and other control paradigms and related complex behaviors even when the individual strategies of all their agents are simple. When agents can share knowledge using any agreed language, within the constraints of the system's communication protocol, the approach may lead to a common improvement. Example languages are Knowledge Query Manipulation Language or FIPA's Agent Communication Language. Systems paradigms: many M.A. systems are implemented in computer simulations, stepping the system through discrete time steps. The M.A.S. components communicate typically using a weighted request matrix, e.g., speed very_important. Min equals 45 miles per hour, path length medium_importance, max equals 60, expected max equals 40, max weight unimportant, contract priority regular, and a weighted response matrix, e.g., speed min 50 but only if weather sunny. Path length 25 for sunny, 46 for rainy, contract priority regular. Note: ambulance will override this priority and you'll have to wait. A challenge response contract scheme is common in M.A.S. systems, where first a who can question is distributed. Only the relevant components respond. I can, at this price. Finally, a contract is set up, usually in several, or short communication steps between sides, also considering other components, evolving contracts, and the restriction sets of the component algorithms. Another paradigm commonly used with M.A.S. systems is the pheromone, where components leave information for other components next in line, or in the vicinity. These pheromones may evaporate with time, that is, their values may decrease with time. properties. M.A. systems, also referred to as self-organized systems, tend to find the best solution for their problems without intervention. There is high similarity here to physical phenomena, such as energy minimizing, where physical objects tend to reach the lowest energy possible within the physically constrained world. For example, many of the cars entering a metropolis in the morning will be available for leaving that same metropolis in the evening. The main feature which is achieved when developing multi-agent systems is flexibility, since a multi-agent system can be added to, modified and reconstructed, without the need for detailed rewriting of the application. The systems also tend to prevent propagation of faults, self-recover and be fault-tolerant, mainly due to the redundancy of components. The study of multi-agent systems. The study of multi-agent systems is concerned with the development and analysis of sophisticated AI problem-solving and control architectures for both single-agent and multiple-agent systems. Topics of research in M.A.S. include agent-oriented software engineering, beliefs, desires, and intentions, cooperation and coordination, distributed constraint optimization, organization, communication, negotiation, distributed problem-solving, multi-agent learning, scientific communities, dependability and fault tolerance, robotics, multi-robot systems, robotic clusters, frameworks. While ad hoc multi-agent systems are often created from scratch by researchers and developers, some frameworks have arisen that implement common standards. These frameworks save developers time and also aid in the standardization of M.A.S. development. One such developmental framework for robotics is given in. See also comparison of agent-based modeling software. Applications in the real world. Multi-agent systems are applied in the real world to graphical applications such as computer games. Agent systems have been used in films. They are also used for coordinated defense systems. Other applications include transportation, logistics, graphics, GIS, as well as in many other fields. It is widely being advocated for use in networking and mobile technologies, to achieve automatic and dynamic load balancing, high scalability, and self-healing networks.